Hi everyone, wanted to keep our long-running Meet the Scientist series going. Here it's a beautiful day. It's September the 20th, 2019. It's around 2 p.m. local time. You've met our colleague, Dr. John Bargar, on the left. He leads the SLAC SFA. We have a new colleague we want to introduce you to. That's Bradley Tolar. He's a postdoc at Stanford University. While we've heard from John before, his research team has both expanded from a personnel perspective, witness Bradley, but also from a site perspective. So John, I wanted to give you a chance to kind of update people on what you've been doing and a couple of your new sites.
Yeah, thanks a lot, Ken. So what I've got here in my hand are some very fine grained organic enriched sediments, which you can see here. And you can also see it under my feet. They go down about 2.5 meters here. These sediments are really interesting because we have redox, so-called redox reactions running inside of them. So that means iron is changing oxidation state between iron 2 and iron 3, depending on the conditions. Nitrogen species are also being transformed among oxidation states and their chemical properties and thermodynamics. Sulfur is doing the same thing. And for instance, contaminant metals, also they're changing their ability to move around. They're actually not changing redox state, but when iron and sulfur get together and precipitate as sulfides, they can pull some very important contaminants out of water and safely trap it. And these sediments are really, really good at forming sulfides when iron and sulfur get together and trap, for instance, zinc.
So with respect to those colloids, sorry to interrupt, their mobility is finite, but it still exists, right? Just because they're forming a colloid and they're trapped in a pore space, they actually can potentially make their way to the river, or is that not the case?
Absolutely. In fact, that's a perfect cue, because what's underlaying 2 meters of this fine stuff is that stuff over there. So underneath of this fine layer, these fine-grained sediments is very highly conductive coarse cobble layer, which is in hydrologic contact with the river, which means the river is actually running under our feet, which means there's an absolutely enormous surface area everywhere that you have these willows. You can just look around here, and you can imagine everywhere that you have a willow, you have these fine-grained sediments, and you have this huge horizontal interface. And the question that we've been asking ourselves is, okay, if you have the river essentially running through this cobble aquifer, it's in contact with the underneath side of these fine sediments. The question that we've been asking is, what if water flowed up? What if water from the river were being sucked up into these sediments? And that would provide a method.
This is some of the coarser grain gravels, by the way.
That would provide a mechanism for bringing water from the river and bringing it up into sediments. You can also ask the opposite question, what if water flowed down? That would be an important way that you could release contaminants as well as nutrients, organic carbon, from these sediments and put them back into the river.
So that then leads me really quickly then to the diversity of sites you started adding on to. They give you an opportunity to look at different hydrologic regimes?
Perfect, exactly, that's right. There's 3 specific hydrologic regimes that we're interested in, which either have very little to no interaction between that cobble and this fine material layers, some that should have downward flow, strong downward flow, and others which should have strong upward flow. And one of the things we're thinking about is classifying all the different floodplain spots on the river here within the watershed in terms of one of those 3 types of behaviors.
Fascinating. So linked to that, of course, is a microbial component. So Bradley, give us a brief description of what you've been doing of late. John had mentioned earlier kind of a manipulation experiment you had performed yesterday. Do you want to describe that?
Sure. So I guess on the general terms, so John talked a lot about the redox processes and shifts between different types of metals and other compounds. So these could be abiotic processes, but they also could be biologically mediated. So that's where I come into the SFA to try to describe whether or not we think microbes are involved. And so yesterday we ran an experiment. Unfortunately, we don't have anything to show right now because we took it down, but basically we simulated rainfall to see what that sort of wet up stimulation might do to the community. And in a previous experiment, John found that it makes it all the way to the cobbles in about 2.5 hours. So we sampled at about hourly intervals, and we're going to see what the microbes do in response.
Very, very cool. So you've looked at it from the transport of the geochemistry side. Will yesterday's experiment be the first time you've looked at the microbial side?
On that specific experiment, yes, but over at the Riverton site and in last year's monitoring of Slate, we've taken microbial samples.
Fantastic.
That are sequencing now.
Fantastic. Well, thanks very much, guys. Really appreciate the time today. It's a glorious day to be working out here.